The Earth before the age of dinosaurs, spanning from its formation approximately 4.5 billion years ago to the late Permian period about 252 million years ago, presents a fascinating epoch in the planet's history. This period, encompassing the Hadean, Archean, Proterozoic, and early Phanerozoic eons, was marked by dramatic geological, atmospheric, and biological changes that set the stage for the emergence of dinosaurs. The early history of Earth, beginning about 4.5 billion years ago, is a story of dramatic transformations, shaping a planet that would eventually harbor life. Earth's formation started with the process of accretion in the early solar system, as dust and rock from the solar nebula coalesced under the force of gravity. This period was characterized by intense bombardment from meteorites, contributing to the planet's mass and heating it to a molten state. The heat from radioactive decay and the impacts kept Earth in a molten form, with the surface dominated by a magma ocean. A pivotal moment in Earth's early history was the formation of the Moon, theorized to have resulted from a colossal impact with a Mars-sized body. This event not only led to the creation of the Moon, but also influenced Earth's axial tilt and tectonic activity. As Earth cooled, a solid crust began to form, although it was continually reshaped by volcanic activity and the planet's dynamic interior processes. Volcanic outgassing released gases that formed Earth's early atmosphere, primarily composed of water vapor, carbon dioxide, methane, and ammonia. The cooling of Earth led to the condensation of water vapor, forming the first oceans and setting the stage for the emergence of life. The end of the Hadean eon saw the planet transition from a hostile, molten world to one with a stable crust, oceans, and an atmosphere, albeit vastly different from the present-day conditions. These early stages in Earth's development were crucial, laying the foundational structure and environment that would evolve over billions of years into the diverse and life-sustaining planet we know today. The emergence of life on Earth, a pivotal event in the planet's history, began in the Archean eon, around 4 to 2.5 billion years ago. During this time, Earth's environment was markedly different from today, with a primordial landscape marked by volcanic activity and a hostile, oxygen-poor atmosphere. It was in this early setting that the first signs of life appeared. Prokaryotes, the earliest life forms, were simple, single-celled organisms without a nucleus. Evidence of these early life forms, dating back to about 3.5 billion years ago, comes from fossilized stromatolites created by microbial communities. These organisms, including bacteria and archaea, thrived in the harsh conditions of early Earth. A significant development in the history of life was the evolution of photosynthesis, primarily through cyanobacteria. This process of converting light energy into chemical energy gradually led to the release of oxygen into the atmosphere, culminating in the Great Oxygenation event around 2.4 billion years ago. This dramatic increase in atmospheric oxygen transformed the planet's environment, paving the way for the evolution of aerobic or oxygen-using life forms. This oxygen-rich atmosphere set the stage for the evolution of eukaryotes, complex cells with a nucleus, about 2 billion years ago. Eukaryotic cells formed the foundation for all complex life, including plants, animals, and fungi. The emergence of eukaryotes, possibly through symbiotic relationships between different prokaryotic cells, marked a significant step towards the development of diverse and complex life on Earth. In conclusion, the emergence of life on Earth was a gradual process that began in an inhospitable environment and led to the development of key biological processes like photosynthesis and the formation of complex cells. These early steps in life's evolution laid the foundation for the diverse ecosystem we observe on the planet today. Spanning from about 2.5 billion to 541 million years ago, the Proterozoic eon was a crucial era in Earth's history, marked by significant geological, atmospheric, and biological developments. This eon saw the Earth's environment stabilize, the atmosphere evolve, and life forms become more complex, setting the stage for the proliferation of life in the subsequent Phanerozoic eon. During the Proterozoic, the Earth's crust solidified and stabilized, leading to the formation of stable continents and the first supercontinent, Rodinia. This was also a period of significant tectonic activity, with the assembly and breakup of Rodinia, which had profound effects on the planet's climate and environments. The atmosphere of the Proterozoic eon underwent substantial changes. The Great Excisionation event, which began in the preceding Archean eon, continued into the early Proterozoic, leading to an increase in atmospheric oxygen levels. This excisionation of the atmosphere was largely due to the photosynthetic activities of cyanobacteria and had a transformative effect on Earth's environment, making it more hospitable for future, more complex life forms. One of the most significant biological developments of the Proterozoic was the emergence of eukaryotic cells. These complex cells, which contain a nucleus and other organelles, are the building blocks of all higher life forms. The appearance of eukaryotes, possibly through symbiotic relationships between different types of simpler cells, represented a major evolutionary leap. Multicellular life also emerged during the Proterozoic, with organisms exhibiting greater complexity and diversity than ever before. This era culminated in the Ediacaran period, approximately 635 to 541 million years ago, which saw the appearance of the first large, complex multicellular organisms, laying the groundwork for the explosion of life in the Cambrian period. The Proterozoic eon also witnessed the formation of the first glaciers and evidence of global-scale glaciation events, known as snowball Earth episodes. These glaciations had a significant impact on Earth's climate, sea levels, and possibly on the evolution of life, as they likely triggered mass extinctions as well as evolutionary innovations. In conclusion, the Proterozoic eon was a period of profound transformations in Earth's geological history, atmospheric composition, and biological diversity. It was during this time that the planet's environment stabilized, the atmosphere became oxygen-rich, and life evolved from simple prokaryotic cells to complex multicellular organisms, setting the stage for the rich diversity of life that would follow in the Phanerozoic eon. The emergence of multicellular life marked a significant evolutionary milestone in Earth's history. This transition from single-celled organisms to more complex multicellular entities occurred during the Proterozoic eon, setting the stage for the vast array of life forms that would later inhabit the planet. Initially, life on Earth consisted solely of single-celled organisms, which had dominated the biosphere for billions of years. However, as the Proterozoic eon progressed, particularly during its latter half, there was a gradual shift towards greater biological complexity. This shift was likely driven by the increasing levels of oxygen in the atmosphere and the oceans, a byproduct of photosynthesis from cyanobacteria and other microorganisms. The first multicellular organisms were simple in structure and likely evolved through a process known as cellular aggregation, where individual cells grouped together to form a larger entity. These early multicellular, as the Proterozoic eon drew to a close, particularly during the Ediacaran period, around 635 to 541 million years ago, there was a notable increase in the diversity and complexity of multicellular organisms. This period witnessed the emergence of a variety of soft-bodied creatures, often referred to as the Ediacaran biota. These organisms displayed a range of body plans and were the precursors to the more familiar forms of life that would emerge in the subsequent Phanerozoic eon. The development of multicellularity allowed organisms to grow larger, develop specialized tissues and organs, and exploit new ecological niches. This biological innovation laid the groundwork for the evolution of plants, animals, and fungi, and was instrumental in shaping the biosphere as we know it today. In summary, the rise of multicellular life during the Proterozoic eon was a pivotal development in the history of life on Earth. It represented a major evolutionary leap, enabling increased complexity, diversity, and specialization among living organisms. This transition paved the way for the explosion of life in the Cambrian period and the subsequent development of the rich and varied ecosystems of the Phanerozoic eon. The Phanerozoic eon, beginning about 541 million years ago and extending to the present day, represents a major chapter in Earth's history, characterized by the emergence and evolution of abundant and diverse life forms. The eon is subdivided into three major eras: the Paleozoic, Mesozoic, and Cenozoic. The Paleozoic era, the first of these eras, spanning from about 541 to 252 million years ago, was a time of significant geological, climatic, and biological changes. The start of the Paleozoic era is marked by the Cambrian explosion, a remarkable period of evolutionary change when most major groups of animals first appear in the fossil record. This event saw a rapid diversification of life in the oceans, with the emergence of many of the major phyla that still dominate the animal kingdom today. The Cambrian explosion was likely driven by a combination of factors, including increased oxygen levels, the development of the ozone layer, and changes in ocean chemistry. Following the Cambrian period, the Paleozoic era saw continued biological diversification during the Ordovician, Silurian, Devonian, Carboniferous, and Permian periods. These periods witnessed the colonization of land by plants and animals, a transformative development in Earth's history. Plants first appeared on land in the Ordovician period, followed by the first terrestrial animals, including arthropods and later vertebrates. The Devonian period is often referred to as the Age of Fishes due to the vast array of fish species that evolved during this time. This period also saw significant evolutionary advancements in plants, including the development of seeds and trees, fundamentally altering Earth's landscapes and atmosphere. The Carboniferous period was characterized by extensive swampy forests, which contributed to significant coal deposits that are mined today. This period also saw the evolution of amniotes, a group of tetrapods, four-limbed animals that includes reptiles, birds, and mammals. The Paleozoic era ended with the Permian period, which was marked by the formation of the supercontinent Pangaea. The Permian period culminated in the largest mass extinction event in Earth's history, known as the Permian-Triassic extinction event, which wiped out approximately 90% of marine species and 70% of terrestrial vertebrate species. This mass extinction event set the stage for the Mesozoic era, often called the Age of Dinosaurs. In conclusion, the Phanerozoic eon and, in particular, the Paleozoic era were times of dynamic changes in Earth's history. This era saw the evolution of life from simple multicellular organisms to complex terrestrial ecosystems, setting the stage for the diversity of life forms that populate the Earth today. The Paleozoic era's end marked a turning point in the history of life, leading to the rise of new species and ecosystems in the subsequent Mesozoic era. Continental drift, the gradual movement of Earth's continents across the surface over geological time, has been a fundamental force in shaping the planet's climate and environmental history. The theory, initially proposed by Alfred Wegener in the early 20th century and later substantiated by the evidence of plate tectonics, explains how continents shift positions on Earth's surface. Throughout Earth's history, the movement of tectonic plates has resulted in the formation and breakup of supercontinents, which in turn have had profound impacts on global climate patterns. One of the most significant supercontinents was Pangaea, which began to form at the end of the Paleozoic era and was fully assembled by the early Mesozoic era. The existence of this vast landmass significantly altered ocean currents and atmospheric circulation patterns, leading to dramatic changes in climate. The breakup of Pangaea, which started in the Mesozoic era, led to the formation of the continents as they are known today. This process influenced the distribution of flora and fauna and played a crucial role in the diversification of life on Earth. As the continents drifted apart, new coastlines were created and shallow seas formed, providing new habitats for marine life. Continental drift also affected Earth's climate through the process of orogeny, or mountain building. The collision of tectonic plates led to the formation of large mountain ranges, such as the Himalayas and the Alps. These mountains not only influenced regional climates by acting as barriers to atmospheric circulation, but also contributed to global climate change by increasing weathering processes, which in turn affected atmospheric carbon dioxide levels. Furthermore, the position of continents relative to the poles and the equator has a significant influence on global climate. Landmasses located at or near the poles, like Antarctica, can lead to the formation of large ice sheets, which reflect sunlight and contribute to global cooling. Conversely, continents positioned near the equator receive more sunlight and can have a warming effect on the global climate. In conclusion, continental drift and the resulting changes in the position and shape of landmasses have been key drivers of Earth's climate over geological time. The formation and breakup of supercontinents, the creation of mountain ranges, and the shifting positions of landmasses relative to the equator and poles have all contributed to the dynamic and ever-changing nature of Earth's climate. Understanding these processes provides crucial insights into the history of our planet and its complex climate system. The Permian period, ending the Paleozoic era, was marked by the largest mass extinction event in Earth's history, wiping out an estimated 90% of marine species and 70% of terrestrial species. This mass extinction event set the stage for the rise of the dinosaurs in the following Mesozoic era. In conclusion, the Earth before the dinosaurs was a world of constant change, marked by the formation and evolution of the planet, the emergence and diversification of life, and significant geological and climatic shifts. This ancient world laid the foundations for the era of the dinosaurs and the subsequent development of the diverse array of life we see on Earth today.